Molti lo sanno, hanno detto devi fare riavviare cose, io
Adesso io cerco sempre di venire qua un quarto d'ora, 20 minuti prima per una...
mettiamo a posto.
Ok? Grazie mille, mi scusi. Ok, sorry for the inconvenience. Non funziona il microfono? On. Non funziona il microfono. Ok ragazzi, un secondo solo. Perché io devo usare questo, no? Che è mute. Let's check with the students at home if they can hear me and see me, and don't worry about the microphone and just start. Students at home, can you hear me? Can you see me?
Yes.
Yes.
You can also hear me because it looks like the microphone doesn't work here. But if you can hear me, that's okay.
Yes, we hear you.
Yeah, we can hear you well.
Okay. Well. Okay. Much better. Okay, let's start with today's class. If I'm not wrong, yesterday we finished with a graph of generic exponential functions, but we didn't begin the natural exponential function. Is that right? Okay. Okay, so this is the most popular exponential function. This is too much. This is the natural exponential function. It is the most popular one for a number of reasons, both related to theoretical aspects and practical applications. Okay, so the exponential function is e to the power of x, where e is a number. It is a number about between 2 and 3, it's about 2.7. Okay, it's not a rational number, it is an irrational number. That is, it cannot be expressed as the ratio of two integer numbers. It comes out from out of a process like this. It is a limit of a sequence. And for a number of reasons, this is the most natural way to define the basis of an exponential function. For instance, this is the only function having the derivative equal to the function itself. Also, it can express very naturally the exponential growth in continuous time. Okay? So this is basically the reasons why this is the most popular exponential function. E to the power of x is also denoted as exponential of x. When you see this is the same notation, a different notation, but the same function as this one. So exponential of x is e to the power of x. I will use both, depending on the situation. E is an irrational number. It is important to show, at least intuitively, the process generating number e. There is an important sequence. A sequence basically is a sequence of numbers that can be obtained by a function of the natural numbers, positive integers, n, and investigating what happens when n becomes larger and larger. Okay, so natural integer numbers, positive integers are 1, 2, 3, 4. Okay, so if I put 1 here, this is 2. Okay, to the power of 1, because n is equal to 1. So the first element of the sequence is 2. Okay, what about the second element of the sequence? If I put 2 here, this is 3 over 2, the base, to the power of 2, 9 over 4, 2.25. Okay? This is the second number of the sequence. What about the third number? It's 4 over 3, very easy to see it, to the power of 3. It's 64 divided by 27. It's 2.37, okay? You can try with a larger number, larger integer, 15 for instance, and you get 2.633. So what happens here? Every time you put an integer here, and you increase this integer, the value that you obtain increases. But it looks like it doesn't increase unboundedly, okay? It has a kind of ceiling, And in fact, it increases, but less and less. And if you put here the number, for instance, 100, you get something very close to this number. So this is a kind of ceiling, okay? It is never reached by this sequence, but you can, by taking n large enough, you can get a number closer and closer to this one. This is called the limit of a sequence, and this is a number between 2 and 3, 2.7, okay? So for some reasons, this is the most convenient base for the exponential function. Of course, since this is a number larger than 1, qualitatively, we have an exponential function of this type, okay? Because this is the case where the base is larger than 1. Sorry, could you start recording the lecture? Oh, you're right, sorry. Start recording the lecture. Transcription, okay. Okay, thanks, thank you. Anyway, this is the basically the natural exponential function. I just explained what is the reason for having this base, and what is this base, number e. It is the limit of a sequence, and the important message for us is that this is a number larger than 1, so qualitatively we are in this case, okay? Base larger than 1, which means that the exponential function of this type is one that increases. It has the whole real line as its domain, but it can only take on strictly positive values, okay? So the range of the function is from 0 to plus infinity, like this one. So this is the representation of y equal to exponential of x, similar to the previous one. If here the scaling factor capital A is equal to 1, right? But if I put capital A here, it is qualitatively the same, except that it intersects the vertical axis at A. So if I had 2 exponential of x, I don't have 1 here, I have 2, okay? But for the rest, it is exactly the same. This is the example of the exponential function y is equal to exponential of minus x. This is can be compared qualitatively to the case where the base is between 0 and 1, because exponential of minus x is 1 over the exponential of x, that is 1 over e to the power of x. Okay, is that clear? And 1 over e is a number between 0 and 1, just because e is larger than 1. So we are in this case, okay? A strictly decreasing function, which has basically a behavior which is the opposite of this one, okay? This is increasing, starts from 0 basically and goes to plus infinity. This starts from plus infinity when x is is negative but very large, because minus x is positive very large, and then it declines and it tends to 0 as x tends to plus infinity. Clear? So we are basically in this qualitative case. Oh, a, the base, between 0 and 1. Okay. Now, we have the logarithmic function. Of course, I mean, you have very different backgrounds, and maybe some of you find this just refresher of elementary algebra, and for some, I guess, this is not the case. Anyway, I just want to stress a couple of things about logarithms and logarithmic functions. Some students get lost when they hear the word logarithm, okay? This is not the case, because logarithm just means exponent, okay? So when we write something like this, I'm going to explain this now, u is the logarithm, this is the natural logarithm of a. We are just writing that e to the power of u, that is the exponential of u, is equal to a. So this is another notation for this one. Here we focus on the exponent, and here we focus on the base, or vice versa. Okay? Let me explain. So the first thing is that logarithm means exponent. And the second important thing is that logarithms, emerge naturally when solving exponential equations. So when we have an equation in which the unknown x is at the exponent, and we want to solve this equation for x, for instance, 5 times exponential minus 3x is equal to 16, then we need logarithms, okay? Logarithms then can be computed numerically with a scientific calculator, but expressing the solution in terms of logarithms is just a rigorous way to say the solution to this equation. Can you understand? It's just a rigorous way to express the solution to that equation, or similar equations. Okay, so there is nothing except a few cases you cannot compute logarithms with the algebra, okay? You need approximations and using the scientific calculator. So what is the logarithm of a number? What we consider here is the so-called natural logarithm, okay? Which has this symbol, Ln, natural logarithm. This means that our reference point is the exponential function, the natural exponential function, not a generic exponential function. The natural exponential function, the one with number e at the base. Remember another thing about the exponential function. When we deal with an exponential function, we raise e to the power of x, and the power of x can be any exponent, any, from minus infinity to plus infinity. Can be minus 1,000, can be plus 1 million. But since the base is positive, the result of this, which is a power, is a strictly positive number. And this is the reason why the image set of this function is from 0 to plus infinity, okay? This is the reason why the image set is the range, is from 0 to plus infinity. So the result of the power is always a positive number. Now focus on the exponent. Take an equation like this. Exponential of u equal to a. We could write here exponential of x equal to a. It's the same. Now u is our previous x. And the base is e. So this is the result of the power. Okay? The exponent can be negative, positive, can be any real number. The result of the power is always positive. So consider a positive number a, strictly positive. And we ask this question. Imagine that a is the result of some power with base e. What is the exponent? Okay, so this is the simple question. I raise e to some unknown exponent, and the result is a positive number. What is the exponent? Of course, in some cases, we can compute it immediately. But in other cases, we cannot compute it. But we can study the properties of this solution to the equation, and that's why we define the logarithm. Okay, so if exponential of u is equal to a, then we define u, the exponent, as the natural logarithm of a. And we write u is the log of a. So u is the log of a just means that exponential of u is equal to a. Since u is the log of a, we can also write this nice identity. The exponential of the log of a is equal to a. Okay? Raise e to the exponent you need to obtain a as the result. Of course, the result is a. Okay. Also, an important remark is that in the equation or expression exponential of u equal to a, u, the exponent, is uniquely defined. Okay, if we have a positive number here, and we solve the equation exponential of u equal to a, we have just one solution. We always have a solution, but just one. So it's uniquely defined. That is, the equation exponential of x equal to a has a unique solution for any a positive. Why? Because if we represent here the exponential function, y is equal to exponential of x, like this, and trying to solve exponential of x equal to a positive number means trying to find the intersections between this graph of exponential of x and an horizontal line which expresses a level, a desired level for this function, which is equal to a. So y equal to a, okay? And you see that since the function exponential is strictly increasing, it never goes like this, okay? It doesn't increase, then decrease, then increase. It is strictly increasing. If you set an horizontal straight line here, you have just one intersection, okay? So there is a unique solution. So basically this means that the natural log of a is unique. The natural log of a is this one, is this u, the solution to this equation, okay? Graphically. Okay. There is other important information can be derived from this graph. For instance, what happens if a, the result of our power, a is equal to 1. If a is equal to 1, this means that this green horizontal line crosses the vertical axis exactly at the point 1, here, okay? If a is equal to 1, then u is equal to 0. So we are just saying that the log of 1 is 0. In a different way, the exponent, I want to raise e to some power, and the result must be 1. Of course, this power is 0. Okay? And another important property is that if a is larger than 1, like in this case, then u is positive. If, with two f, it means if and only if. Okay? If a is less than 1, so if the crossing of the vertical axis is below 1, like this, you see that the solution is negative, okay? So if a is less than 1, between 0 and 1, of course, u is negative, okay? So basically, the log of a number is 0 if this number is 1, it is negative if this number is between 0 and 1, it is positive if this number is larger than 1. Of course, another thing that we see from this graph is that the log is a strictly increasing function. If the natural log, since the base is larger than 1, is strictly increasing. I mean, if you increase if you increase a, because we have the log of a, okay? If you increase a, start from a equal to 0 and increase a, so increase the level of this horizontal line, you get solutions that move from the left to the right. Okay? So the log is an increasing function of the argument, of its arguments. We have a lot of information from this. The log is an increasing function. So what is the domain of the log? The domain of the log is, remember that the log is applied to the result of the power. Okay, the result of the power is strictly positive. So its domain is strictly positive numbers. Its range is from minus infinity to plus infinity, because we can get solutions that range over the whole horizontal axis. So its range is from minus infinity to plus infinity. Its domain is strictly positive real numbers. It is an increasing function. It takes the value 0 when the argument of the logarithm is 1. Before 1 it is negative, after 1 it is positive. Then there are, of course, other properties. Don't look at the properties here, just look at the graph here. Next we discuss these properties. So this is the representation of the function y is equal to the log of x. Okay? Now I'm representing a function, so my independent variable is called x. Okay? And y is the log of x. It is a strictly increasing function. It is defined only for positive values of x, but on the other hand, it can take on any real number as the result. When x is 1, the log is 0. After 1, on the right of 1, it is positive. On the left of 1, it is negative. Why is that? We see here that when x tends to 0, the logarithm tends to minus infinity. It can be understood here. Our x is the level of this line. If you take a line which is very, very close to the horizontal axis, your solution is negative, very large, okay? So when x tends to 0, the log tends to minus infinity. And when x tends to plus infinity, the log tends to plus infinity as well. And it can be proven that the log is, it is not linear, it is not convex, it is concave, okay? It has a behavior like this. And this is one of the other functions. The log embodies the properties of being increasing in concave, like the square root, for instance. So this is another very popular function used to express, for instance, so-called principle of saturation, okay? So utility and so on, okay? So the increase of utility is positive, but the rate at which utility increases when you increase the consumption of a certain good is diminishing, okay? So it incorporates the so-called idea of decreasing marginal utility, okay? And this is very popular in economics because it's one of the simplest functions incorporating this property. All the properties of the log, this is just a refresher. To understand the properties, just remember that logarithm means exponent. All of these can be derived by the corresponding properties of the exponential functions. We all know that the log of 1 is 0, just because exponential of 0 is equal to 1. The log of e is 1, just because e to the power of 1, or the exponential of 1, is equal to e. So the log of e is 1. The log of 1 over e is minus 1, because 1 over e can be expressed as exponential of minus 1, okay? So the log of the exponential of minus 1 is minus 1, okay? Should be here. This is an important an example that is just to provide to give you a message, an important message. Every time you solve, even starting from these simple tools, when you solve a problem, a useful strategy is try to form expectations about the solution. Okay, try to before using the scientific calculator, okay, or applying a method for the solution, just try to form expectations. For instance, in this case, the log can be computed with a calculator, scientific calculator, except in a few cases. But we can understand almost everything about its behavior, okay? For instance, this question is, without using the calculator, is the log of 4 larger than 2? Remember that we have a power, a sequence of powers, and the corresponding exponents, okay? The base is the same, it is e. So what we know is that 4 is between e and e squared. Why? Because e is 2.7. Just remember that e is about 2.7. Okay? And e squared, since e is larger than 2, e squared is, of course, larger than 4. In fact, e squared it is 7.3. But the most important message is that in exponential of 2 is larger than 4, because the base is larger than 2. So, remember that 4 is the result of a power with a base e. So e, we are sure that e is less than 4, which is less than e squared. So the same ordering must hold also for the exponents, the same ordering. So the log of e, which is 1, is less than the log of 4, which is less than 2, because 2 is the log of e squared. Okay? So we know, without using the scientific calculator, that the log of 4 is between 1 and 2. Okay? Which is really important. I mean, forming expectations using a little bit of theory is really important for the solution of the exercises. Because then, when you switch to the computation, you have a kind of reference point, and you can compare your result with the reference point. And this is also very useful to make possible corrections to your solution. Okay, other properties. This is another properties. It is often stated by saying that the log transforms products into sums. Okay? And vice versa, the exponential function transforms sums into products. What is the meaning of this? If we have two positive quantities, x1 and x2, strictly positive, and we have their product, x1 times x2, then the log of this product, the natural log of this product, is just the sum of the logs of the two factors. Similarly, if we have the log of x1 over x2, so the ratio of two positive quantities, then the log of the ratio is the difference of the two logs, okay? Transforms products into sums, ratios into differences. Very similarly, is this clear to all of you? Already known standard tools, any doubts about that? Okay, so of course, why do I need to impose x1 and x2 larger than 0? In principle, the product is defined also if x1 is minus 2 and x2 is minus 5. The product is 10, but of course I cannot apply this property because the two factors are negative, okay? For example, the log of 10 is the log of 2 plus the log of 5. Okay, and now assume, for instance, here that x1 and x2 are equal to the same number, x. Here you would have x times x squared. So the log of x squared would be equal to the log of x plus the log of x. And we have the final property here. The log of x to the power of p is just the product p times of the same number x. So it is p times the log of x. Okay? X, again, must be a strictly positive quantity. Then we have some identities. One, you already know it. X is the exponential of the log of x, and the log of the exponential of x is equal to x. By the way, the last one can be derived also from this property, because the log of a power with a positive base is the exponent times the log of the base from this property. Okay, so the exponent is x, the log of the base is the log of e, which is 1, So the result is x. Okay? Okay, now we have some examples. Next, after these examples, I'm going to show you. So you may wonder why I spend time on elementary functions and exponential and logarithmic equations, because we need to use them very often. Okay, so this is the reason why I spend time. And also it is I want to make some pressure on you to become more and more familiar with elementary functions, because most of the times you need to deal with these functions or slight modifications of them. And unfortunately, also most of the mistakes that I see in the written exams, written examinations, come from a mistake related to elementary functions, not to partial derivatives. Okay, in general, students can compute the partial derivatives, but basically cannot solve a simple equation like this one equal to 0. Okay, which is quite strange, but this is what I always see. So but the main reason why I stress, I emphasize this function is that we use them very often. And next I will show you, after this, before starting a new examples, I will show you some samples of the partial exam and the full exam, just to let you know what you should expect from the examination, okay? What types of exercises. Okay, so the first exercise is this one: provide a qualitative graph. And another reason why I use this one variable function is that, okay, the first part of the course then focuses on multivariable functions and multivariable optimization. But you may need to solve equations of the type f of xy equal to 0. So you have to solve equations to get the explicit expression of y as a function of x, which is similar to this one. And also, these kind of models are used for one-dimensional differential equations in the second part of the course. So our differential equations will use basically one variable functions of elementary types, but you need to master them quite well. Okay, so provide a qualitative graph of this function and solve the equation f of x equal to 0. Okay. To provide a qualitative graph, in this case, we don't need the usual techniques to study the function. We don't need derivatives to study when the function is increasing or decreasing, because everything is based on an elementary function, which is exponential of minus x, basically, or exponential of minus a constant times x. So let me start from the base case, exponential of minus 1/3 x, like this one. Don't worry about a 1/3 here. It's like, qualitatively, this is like exponential of minus x, which is an elementary function. If x is equal to 0, it takes on the value 1. Okay? For the rest, it is identical to exponential of minus x, so it has this behavior. Okay? Just look at the elementary function exponential of minus x before. But in our function, we have 1/2 exponential of minus 1/3 x. So we have 1/2 here. But we can build new functions from old ones by just rescaling everything, okay? If I have a multiplicative constant which is positive, qualitatively nothing changes except the fact that now, when x is equal to 0, the function is worth 1/2. Not 1, 1/2, okay? Is that clear? However, in our equation, we don't have 1/2, we have minus 1/2. No worries. it's the negative of this one. And the negative of this one is the same graph. It's a mirror image of this graph with respect to the horizontal axis. So it is the red one here. So the intersect, this is decreasing, this is increasing. Of course, it is a negative. This intersects the vertical axis at 1/2. This intersects at -1/2. Tends to 0 from the positive values, tends to 0 from the negative values. And also here, remember, when x tends to -infinity, you should expect that this explodes in this way, okay? And also this one explodes towards the negative values. Okay. But in our function, we don't have this, we have +3. Okay? When you add a constant to a function, you just shift the graph upwards or downwards, depending on the sign of the constant that you add. You shift this by an amount equal to the constant. Okay? Our constant is +3, so we shift this red graph upwards. At any point x, the graph is the same, but the vertical coordinate is increased by 3. So we have this graph. Since the intersection point here was -1/2, this is -1/2 +3, so 5/2. Since here it is upperly bounded by the horizontal axis, this will be upperly bounded by another horizontal line, which is the horizontal axis +3. So y equal to 3. Okay, so this is the limit of this new function. And also remember that this goes towards -infinity here. And also this one, this blue one, goes to it's not represented here, it goes to -infinity. Okay? So there will be some point where this intersects the x-axis. Is that clear? And this point will be unique. Why? Because this is strictly increasing. Strictly increasing. Also, this one is strictly increasing from -infinity to 3. Okay, so there will be only one intersection point with the x-axis. I go back to my previous recommendation. Try to form expectations about the result of your computations. You will find an intersection with the x-axis, but if your reasoning is correct, you are sure that your intersection will be negative. Okay? So the result of your equation, f of x equal to 0, which means the point where it intersects the x-axis, will be a negative point. Okay? So if we, by mistake, you find a positive point, just go back and redo your computation. Okay, so this is the equation, f of x equal to 0. So we write the equation. We can write, usually what we do when we have equations involving exponentials, we must arrive at a situation like this where we have exponential of an expression containing x on one side and everything else on the other side. Okay? So, 1/2 exponential minus 1/3 x equal to 3. Multiply both sides by 2, exponential minus 1/3 x equal to 6. Okay? So now we take logs of both sides. Switch to logarithms. What is a conceptual reason for that? We have the equality between two powers. This 6 can be regarded as the result of a power. Okay? The base is larger than 1. Okay? So if the results of the two powers are equal and the base is the same here and here, also the exponents must be the same. So take logs means rewrite the same equation in terms of the exponents. The exponent here is clear. What is the exponent here? It is the log of 6. Okay? Why is it the log of 6? Because e raised to the power log of 6 is exactly equal to 6. So the exponent here is the log of 6. So we switch to the corresponding exponents. Minus 1/3 x is equal to the log of 6. This is the meaning of taking logs on both sides, which is a very common way of solving these equations. Okay? Then x is equal to minus 3 times the log of 6, which is equal to minus 5.38. And this is here I'm completing the representation of the previous function, this blue one. Okay, it is here. This function is like this, and it is upperly bounded by y equal to 3, which is the limit as x tends to infinity. And then it goes to minus infinity, and of course it intersects the x-axis at a negative point, which is equal to minus 5.38 about. I hope that this is clear enough. So exponential equations of this type are very common, at least being able to solve for these quantities equal to 0, okay, understand where they cross the axis, understand their broadly means qualitatively, their behavior. Here is another example. F of x is equal to 9 minus 4 over 9 x to the power of minus 2, where x is a positive quantity. So here I don't consider the case where x is negative. Of course, you know that x cannot be 0, otherwise this quantity is not defined. Since, for instance, this could represent an applied model where x is a positive amount of something, I restrict the analysis to the case where x is strictly positive. I do the same as above. What is the shape of the curve 4 over 9 x to the power of minus 2? It's a constant times an elementary power function, okay, which is 1 over x squared. The constant is 4 over 9, positive, okay? Let's start from this one. X to the power of minus 2 has this behavior. It is the brown curve, this one, qualitatively. And nothing changes if I multiply by a positive constant here. 4 over 9 x to the power of minus 2. It is, again, this one, qualitatively. So what you have to keep in mind is this. Two things. 4 over 9 x to the power of minus 2 is like 1 over x, 1 over x squared. Power functions with the negative exponent, and possibly a positive constant here, start from plus infinity, decrease in this way, and then approach the horizontal axis. Remember the elementary functions, the graphs of the elementary functions seen yesterday? Of course, when x, this is defined for positive x, but when x gets closer and closer to 0, 1 over x squared becomes positive and larger, okay? So this is the reason why we have this. Now, we have minus 4 over 9 x to the power of minus 2. So just take the mirror image with respect to the horizontal axis, which is the red one here. Then we add plus 9, and this means that this qualitative graph is not very good, but this means that in principle we should shift this upwards exactly by 9, okay? Each point of this curve must be shifted upwards by exactly 9. Maybe you can't see this here, but in principle, remember that this goes towards minus infinity very steeply here. So when you increase by 9, it looks like the two curves on this part are closer to each other than here, okay? Anyway, shift this upwards by 9. Remember that now this red curve was approaching 0 from the negative numbers as x becomes larger and larger, okay? This one will approach 9, okay? This one becomes negative larger and larger as x approaches 0, and this one does the same, but since it starts from above the horizontal axis, it must intersect this axis at some point. Okay? So there will be only one solution also in this case. If you restrict the analysis to the case positive x, of course, there will be only one solution. And we can compute this solution. F of x is equal to 0 if, of course, 4 over 9 x to the power minus 2 is equal to 9, which means x squared equal to 4 divided by 81. Okay? So x star, the solution, is equal to 2 over 9 here. Okay, so this is a really useful way of looking at elementary functions, trying to build new functions from old functions where the old functions are basically elementary functions that you know already. In this way, you don't, in many cases, you don't even need to study the function with the traditional techniques from a scientific high school, I mean derivatives, limits, and so on and so forth, because we are dealing with elementary functions that are useful for applications. Okay, so you know that this kind of functions, in principle, when you study this high school or basic mathematics course at the university, in your bachelor degree, you in principle study the behavior for any x, positive or negative. Since x equal to 0 is outside the domain of the function, here we have the typical case of computing the limits as x tends to 0 from the right or from the left, which in general it may be different, it may be the same, it depends on the function. But we don't find this kind of problems here, because we always restrict our analysis to the economically meaningful range of these quantities, okay? So we only have to understand what's the behavior as x tends to 0 from the right. Okay, so this is the last slide of this first set of slides. But now I want to show you something about the examinations, okay? So remember that, I hope that now you understand now, and also thanks to the next examples, you can understand very well why I stress this kind of tools. Let me start with the midterm exam last year. Okay, you may. The exercise in general, the exercises are really simple from a computational viewpoint. So, I mean, you can use a scientific calculator, but it's not really useful because the computations are really simple. And I don't want you to write down the result in terms of a numerical approximation, as the one that you find from computing it with the scientific calculator, but when it is possible to derive the analytical form, for instance, if the result is the log of 2, I want you to write down the log of 2, because this is the proof that you were able to solve the exercise, actually, okay? So, this is the midterm exam. Remember that the midterm exam is about the first part on two variable functions, basically, and also everything about two variable functions. Not just the derivatives of two variable functions, not just the finding maxima or minima of two variable functions, but also computing simple quantities. Rate of change, partial rate of change, elasticity, partial derivatives, log derivatives. All of these measures of change are really important also in applied economics, because applied economics is also should be important for you, okay? So they don't even use finding maximum or minimum of strange functions. The functions are really, really simple. They are most of the times concave functions or convex functions for minima, so I don't stress very much second order conditions, for instance, but just first order condition, the Lagrangian of a problem of constraint maximum or minimum. like in this case. Okay, here we have a simple two-variable function, which is the sum of two functions of x and y. The first question is writing down the equation of the level curve. The level curve, if this represents a utility function, this is an indifference curve. If this represents a production function, this is called isoquant. Okay, so these are very common quantities in macroeconomics. So writing down the equation of the level curve, passing through some point, computing the derivative along this level curve. Okay, this is the implicit function rule of differentiation, which is will be part of the program. Determine the optimal solution to a simple constraint maximum problem with a linear constraint. In terms of a parameter m, which represents the budget per unit time, the available budget per unit time. So what we get here is, for instance, a solution in which the optimal quantities of x and y depend on m, okay? Because it's a parametric problem. Then, since this is a particular case in which there may be a corner solution, there is an additional question which imposes that the quantities in the solution be non-negative, okay? There may be some cases in which the solution lies at the corner of the set of possible choices. This is the first exercise. This is another example on a very popular function, which is a function of two variables, which is separable in terms of ratios. Okay, so it has a nominator that depends on x, denominator depends on y, and what I ask here is to find the linear approximation of this two variable function near a certain point. Okay, this requires knowing the concept of differential of a two variable function. This is another measure of change. Very typically, we have functions expressed as products of functions of x and functions of y. And very typically, we need to compute the so-called partial elasticities of this function. When computing partial elasticities, we have to take logs, basically. Logs transform products into sums, and then it is easy to compute the elasticities, okay? And this is an exercise which is really useful, okay? Compute the partial elasticities of this function. And then another exercise was about computing the first and the second partial derivatives of this utility function. So nothing is difficult from a computational perspective here, but you must know what you're doing. This was the midterm exam. So you see that, for instance, here, for the level curve, writing down the equation of the level curve, computing the derivative of the level curve, you have two different ways of doing that. If you are able to solve explicitly y for x, a level curve is something like this value equal to a constant, okay? Then you have an equation in x and y. If you are able to solve y for x, which means being able to solve equations, okay, you can compute the slope of the level curve directly. Alternatively, and in general, this is easier, you apply the implicit differentiation rule. So you leave the equation like this, you don't solve y in terms of x, and you compute the derivative. There are two different ways. But the computations are not really difficult in this case. You can choose any of them. In other cases, it's very difficult to solve y in terms of x, and you need to apply the implicit differentiation rule. But in general, there is at least one way to solve these exercises that is not demanding from a computational viewpoint. It's really easy. Okay, so this is the first example. Here are other examples. This was the midterm exam. Just have a look at maybe the second midterm exam, the second partial, just to let you know what you should expect from the second partial exam. Remember that the second partial exam is about basically dynamics and integrals, okay? This is a simple, okay, these are three simple dynamic models in which the derivative, the time derivative of a variable x has some expression that depends on time, okay? You must solve for x of t. You must find the trajectory of x from a given initial point to time, generic time t. In this case, you must solve an integral. The initial point, the initial level of the variable must be x0, generic. In this case, you must solve an integral. In this case, you must solve a simple linear differential equation, autonomous, so with constant coefficients. In this case, you must solve a linear differential equation with a time-varying forcing term. Okay, so linear differential equations of simple types will be really important in the second part. In general, we have the structure of the examination is as follows. There is one exercise 1, which is sufficiently, I mean, it has a number of questions. It is a full exercise on some topic. And for that exercise, you are required to provide a detailed step-by-step solution. So I want to see all the solution steps, okay? Maybe with some short comments, just to explain what you're doing. In the second part, there are a number of short exercises for which you have only to write the final result, because these refer to basic computations. They are basic exercises for each topic. I mean, it's not. I mean, of course it's possible to not being able to solve them or solve them in a wrong manner, but you have a lot of tools to check immediately that your result is correct. So you are required to provide only the final result and not the intermediate solution steps. Okay. For instance, computation of this integral, which is an almost immediate integral, and the computation of this integral, where in general you can also write an intermediate step here, which is the indefinite integral, and then compute the definite integral. So you have basically to provide two steps here, not just the final result. A simple difference equation. Remember that for each of these exercises, you have a way to check your result. And this requires knowing a little bit of theory. And then there is a final exercise, in general, on matrices, simple computations. Here we have a 2x2 matrix, a vector. I want to compute a product, a quadratic form, to find the eigenvalues of this matrix, and then to solve, to determine the saddle part of a simple dynamical system defined by this matrix, basically, okay? So there is nothing difficult. I mean, the computations takes really few minutes, but you must know what you're doing, otherwise you cannot solve it. This is an example of the second partial, and this is an example of the full exam. For instance, the one of February. Oh, this is too easy, I don't want to show you that. The one of September. This is a full exam. Again, full exam includes exercises from both. The first exercise, the one that requires a full solution steps, can be on the first part or on the second part. In general, it is on the first part. In general, but it can be any exercise on the first part or on the second part. This is a two-variable function where it is required to compute the partial derivatives of this function, the partial elasticities, and the partial elasticities of another function, which is the previous one, times an expression that depends on x. Okay? Next, find the optimal solution to a constrained maximum problem in which I use the same function to be maximized under a linear constraint, again. both if m is equal to 4 and if m is generic, and then computing showing that the slope of the level curve at the solution point, which is known as marginal rate of substitution in macroeconomics, is exactly equal to the slope of the budget line, which is really easy. And to do that, you need to apply the implicit function derivative, the derivative of implicit function. So this was the exercise 1 of the latest exam. What about the short exercises? In that particular exam, the short exercises, those requiring only the final answer, where on the second part and on simple matrix algebra, okay? 3 integrals. One is indefinite. 2 are indefinite integrals. 2 integrals, sorry. One is indefinite integral, and the other one is both indefinite and a definite integral. Or even 1 hour and 40 minutes. So almost everyone delivers the examination before the deadline. Okay.
But will it be possible to do that?
Okay. This is a question, and just I didn't mention it last time because currently there is a big problem with this mixed. I should not record what I'm saying, but I mean, you know, it's clear that we must arrive at some point where we have to choose one way for the examination, okay? Not 2 ways, not both, because there is a big problem of fairness. Also, even assuming that all students are perfectly honest, there are 2 different ways of doing the exam. So, currently it's mandatory to leave open possibility for students to take the exam online, the online examination, but it is optional to add also the examination in the room. So my intention is to leave only the online examination for all of you, okay? The online examination. But we are waiting for further recommendations from the University of Bologna. So what about the other? I mean, what about the other courses?
Nobody has specified yet.
Not specified yet. The same reason. So, but I'm explaining to you the reason why nobody specifies. There is a big problem with keeping alive both the online examination and the examination in presence. There is a big problem, which is not just the waste of time. I mean, not just a waste of time. There is a problem of the exam, the way the exam must be structured. Okay, so anyway, I will keep you informed about that. Okay.
Yes, sir.
Yes?
Excuse me, I have a question. But will we have specific lessons for the exercises or not?
Yeah, this is a good question, of course. And it is my intention to start the exercise classes not from the first week, not from the second week, but at least from the third week, because now what we are doing now is just a refresher of And these are elementary concepts, elementary tools. And we have exercise classes, and from Dr. Marzia Dalla Venezia, who has been working in this course with me also last year, 2 years ago. So we prepare exercises that can be useful, can strengthen what you learn in the class. But I would say starting from the third week. And
Okay, perfect. Thank you.
maybe intensifying a little bit before the partial exam and before and at the end of the course. Okay. So
Thanks.
you don't really need exercise classes now. Also because I'm leaving all the material online. Okay. Okay. Now I want to show you a few more examples about this kind of computations. Okay, let me start a new one. Then I will leave you. I will leave you what I'm writing now as an additional PDF file. So suppose that you have this two variable function. Don't get scared about two variable functions. It's just an expression that depends on two variables, okay? But then we want to solve this expression in terms of one of the two variables. So it's again solving equations. But they are very typical examples again. So the first one is this. Since next time we will start with two variable functions, so it's time to write down these expressions. F of xy is equal to the natural logarithm of alpha plus x plus the natural logarithm of beta plus y. Okay? Where alpha and beta are positive parameters. This is a function of two variables. This means that I can select a given amount of variable x, a given amount of variable y, and I get the result. This may represent, for instance, the utility from consuming the amounts of two different goods. Okay, in many applications, we need to find all the possible combinations x and y that give as the result the same value for the function. So in some cases we need to solve f of x, y equal to a constant c. Okay? Which means, suppose that this is a utility function. If you consume a certain quantity of good x and a certain good 1, which is called x, and a certain quantity of good 2, which is y, we get some utility that depends on my consumption choice. Are there different combinations of x and y that give the same level of satisfaction, the same level of utility? This is called an indifference curve in this case, okay? In this case, this is a generic expression of a level curve for function f, finding all the combinations of x and y, yielding the same level of function f. Of course, this is an equation, log of alpha plus x. Of course, also x and y are positive values of the variables, or maybe also no consumption. Also 0 because there is a suitable positive constant here, alpha and beta. So the argument is always positive here, okay? They are very common tricks and models to produce this kind of functions, okay? So the log of alpha plus x plus the log of beta plus y must be equal to c. Then I anticipated to you that we don't need to solve it in principle, but we can study the behavior of this quantity using the implicit differentiation rule, for instance. You can understand the behavior, the slope, for instance, of this curve at a certain point xy. But now we are dealing with equations. Let's try to solve it. So I want to express y as a function of x. So I write, first of all, the log of beta plus y is equal to c minus the log of alpha plus x, right? Then I interpret this as, remember the solution to the exponential equations? We had to take logs of both sides. Now we have logarithms. If you want to solve it, we have to take exponential of both sides. So now regard these questions, just idea. We have to take exponentials of both sides. So regard them not as the result of the powers, as before, but as the exponents. Suppose that these are the exponents of the same power with base e, and take the powers. So I write, this is an intermediate step that I do now, but in principle you can avoid it. I should write exponential of the log of beta plus y is equal to the exponential. Now you understand why we write not e to the power of, but exp of, because now I'm writing e to the power of, but there is a big expression at the exponent, e to the power of c minus the log of alpha plus x. Clear? This is the next step. Now, what is the result of raising e to this power? Beta plus y. Okay? And what is the result of raising e to this power? It is the exponential of c. Remember that first of all this is an exponent which is split into parts, two additive terms, okay? Properties of exponentials, the exponential of this exponent is the exponential of c times the exponential of minus log alpha plus x, okay? I'm doing all the steps now. Okay? Now, here we have again beta plus y is equal to the exponential of c times what? So what is, okay, so if I'm raising, so remember that this one can be written in this way. Okay? It's clear this is a property of the exponents. So this is the log of 1 over alpha plus x. Clear? So here I'm raising e to the log of 1 over alpha plus x. What is the result? Of course. 1 over alpha plus x. Okay? Now, C can be, in general, since the result of the logs can be positive or negative, in general we don't worry about utilities taking negative values, because utilities usually are just an index. So we can just set the interval where this index ranges. We can have also negative utilities. What is important is the ordering of the values of utility, okay? So in principle, C could be also a negative number, but the exponential of C will always be positive. So we usually write this exponential of C as K, where K is a positive number, okay? So here we have the final solution, which is Y is equal to K over alpha plus X minus beta. Okay? This is the solution to our equation. So basically, what we found here is the explicit solution to this equation. And there is another way to solve it. I want to show you. So basically what we see here is that in principle the relation between y and x is very simple, okay? It's y is equal to constant divided by constant plus x, which is basically a hyperbola, minus a constant. So it's really simple. We can do that also in a different way. When we want to solve f of xy equal to c, we can switch to the exponents before doing this step, okay? You can switch to the exponents here. So for instance, that was the log, so also the log of alpha plus x plus the log of beta plus y, time for a break, just 1 minute, is equal to c. C can be any real number. Take the exponential of both sides. K is the exponential of c. This symbol means equal by definition, okay? We set it equal to exponential of c, okay? And it is positive. Now, this is just the exponential of the log of the first times the exponential of the log of the second. So this is alpha plus x times beta plus y is equal to k, which means beta plus y equal to k over alpha plus x. So y is equal to k over alpha plus x minus beta. Much easier in this case. Much easier, of course, if you have to solve this for the examination, use this second. But this is useful to show that we have properties of logarithms here that lead to the same result, of course, okay? So it's really useful to understand the properties of logs. Well, this is a very significant and very meaningful example because these kind of functions are very common. Okay, let's take a break now. Questions? Okay. Let's take a break. 15 minutes break, okay?
Okay.